Swayam Prabha. Digital India. Educated India.
Friends, today we will be starting a new topic on pipe flow, that is what we call as pipe network analysis. Well, in the last class itself we did refer to this particular topic while we were discussing say pipe in series or pipe in parallel. Then we were saying that okay, a section of pipe or a stretch of pipe, suppose it is in series or in parallel, but this may be a part of a bigger network. So, of course, not only that issue, but suppose a single pipe, several single pipes can form by joining in the form of a network. Well, so today we will be discussing how this pipe network is existing in different field of say water distribution system, and then how the hydraulics of pipe network is important and how we analyze those things. Well, before going to pipe network, let us see in the last class what we did. Say we were studying practical need of connecting pipes in different pipes of different diameters in series and in parallel. Well, then of course we did discuss how we calculate the head loss in pipe in series, and then of course we were studying how we calculate the pipe loss, the head loss in pipes when they are in parallel. And of course we did refer that parallel does not mean that they should be physically parallel, but the concept of connection is parallel. Well, that we did discuss, and of course again we were discussing that a bypass, say in a main pipe there can be always bypass, and then how by measuring the flow in a small bypass we can have idea or we can know about the discharge in the main pipe. Well, after this now we can move on to the analysis of pipe network. Well, in many water distribution system, the pipelines conveying the water generally branch out and form loops of complex manner. Well, so it is our common experience that whenever we see a pipe distribution system, suppose in city water distribution system, then we see that pipes are forming a network sort of things, and a network is carrying the pipe for carrying discharge to different part. Well, then this complex layout of pipe is called pipe network. Well, now what is the main problem in analyzing this pipe network? The main problem is that okay, when there is a single pipe, say when we were discussing a flow through a single pipe, friction etc. we were discussing, then one point was very much clear to us, that which is the upstream direction, which is the downstream direction. Then that means from which point to which point the water is flowing. Well, but even when the pipe were in series, then also it was very much clear that from which side the flow is flowing. And when the pipes were parallel, then also the direction of flow, there were no confusion about that. We were very much sure about that. But in pipe network analysis, so different network can be there. Well, let me just draw one network of this kind. Say this is one simple network. Say water is coming from this type, this part, and then it is moving this way, and then this way a part is going. Well, from here suppose some water is going out also maybe, then this water is finally going out from this point again, and then water in this pipe is in this direction, in this pipe is in this direction. But suppose if I ask that, okay, what will be the direction of flow in this pipe? This can be that water may be moving this way, then it is coming this way, and then it is moving in this direction. Or it can be either other way also. Say water is flowing in this direction, then it is moving this way, then it is going this way, and then it is going out from this particular point. Well, so the direction of flow in this particular pipe is not known. This is just a network we are drawing where we have only two loops. Say this is one loop, this is another loop. But there can be network, or there will be network in real situation which will be containing several loops having this sort of common pipe. This pipe is common to this loop as well as that loop. So in this pipe, it is very difficult to say what will be the direction of flow in this particular pipe, and that's the major problem. So determining flow direction in all pipes of the network by simple observation is not possible, and the uncertainty about the flow direction makes the problem of hydraulic analysis of pipe network more complex. Now, what is hydraulic analysis? That will be coming later, but this makes more complex. Well, the hydraulic analysis of pipe network is achieved on the basis of following condition. Well, hydraulic analysis means, say when a discharge Q is coming, and say we want that Q1 discharge should be flowing in this direction and Q2 should be the final flow, then our interest is to know that how much will be the flow in this particular pipe, or in this particular pipe, or in this particular pipe, or in any of the pipe. This is one region, and then we may be interested to know what will be the head available at this point. Suppose we want a discharge Q at this point, but this discharge will have to be raised to a certain head. Then our interest is to know that how much head will be available at that point. So that is also one of our interest. Then another interest is that, well, say this diameter, we are not knowing, suppose what should be the diameter. If we fix a pipe of different diameter, then although we need water of say Q1 here, it may happen that this Q1 water is not available there, and as such we will not be getting the required amount of discharge at that point, and that we can achieve by adjusting the diameter of the pipe. Well, so those issues are important, and analyzing those things and designing the pipe network, all those are coming as a part of hydraulic analysis of pipe network. Well, and this is achieved. This hydraulic analysis is achieved on the basis of following conditions. Okay, what are those conditions? So basis of hydraulic analysis, the first condition is that the continuity equation must be satisfied. Now, where continuity equation must be satisfied at every node, that we can write. Means, say this is a junction point. Node means, okay, let me call this as a junction, at a junction point. Now, so this is a junction, and suppose a amount of Q1 is coming in this direction, Q2 is going in this direction, and then Q3 is going in this direction. Now, what this continuity condition is, that Q1, that is which is coming into this particular point, this is a node, suppose Q1 is coming into this, so Q1 and what is going out, this must be equal, Q2 plus Q3. That means the flow coming into a junction, say flow coming in is equal to flow going out. And that is true not only for a point which is just an inner point, or which is, suppose each pipe are a part of the network. Say if I draw a network like this, again that same network, simple network, then suppose at this point if water is coming here, going there, and then it is also, suppose from this side it is coming, then we can say that Q1, Q2, Q3, in that case we can say that at this point Q1 plus Q3, both are coming in, is equal to Q2. Well, then again suppose, well, this is the discharge which is coming in, Q, and this is the discharge which is going out, say Q out. Now at this point at this point say discharge through this pipe which is coming in, and this pipe it is coming in, and going out is this point. Well, so this is suppose Q4 and Q5, let me give this name as Q out. So what will be the continuity condition? We will say at this point that Q4 plus Q5 must be equal to Q out. Okay. Similarly here also, if there is a discharge like this, say Q6 is going, or suppose let me give a name, say Q6, okay, this be Q6, then say this is Q7, then what we can write, the continuity condition, if I write for this particular point, then what we can write, say Q7 which is coming in minus Q3 which is going out minus Q4 which is going out, and Q6 is also going out, minus Q6 is equal to 0. Well, or say we can say Q7 is equal to Q3 plus Q7 is equal to Q3 plus Q4 plus Q6. So this is what is continuity condition, and this must be satisfied. That is the most important point, and based on this continuity condition, first we assign a logical value of discharge in each of the pipe during our pipe network analysis, and after that of course we need to do iteration based on other condition. Now let us see what are the other conditions that need to be satisfied. Well, the other condition, that is the basis of hydraulic analysis, based on already one condition we have discussed. Then second condition, that flow in each pipe satisfy the head loss equation. Flow in each pipe satisfy the head loss equation, that is the Darcy-Weisbach equation, and of course we normally use the Hazen-Williams equation here, not the Hazen-Poiseuille equation, Hazen-Williams equation, and this is not just we can derive from here directly as, say, head loss is, say, proportional to Q to the power n, that way we can derive. Well, we know Darcy-Weisbach equation, that condition what we discussed earlier regarding Darcy-Weisbach equation, for what condition it is applied, and those conditions we assume that this is satisfied. Now considering that, what we have, that is head loss HL is equal to, say, FL V square by twice G D, that is the Darcy-Weisbach equation. Okay. Now starting from this, what we can write, that HL is equal to, say, FL, F is the friction factor as we know, L is the length of the pipe, and then V is the velocity of flow. Of course we talk about average velocity when we talk, say, velocity of flow in a pipe. At the central line the pipe flow velocity will be more, but we are talking about the average velocity in the pipe, and then D is the diameter of the pipe, G is the acceleration due to gravity. But this V square can be written as, say, Q square by area. Area is nothing but pi by 4 D square, so it is whole square that we can write. So what we can write this value, say V square we can write Q square by A square, area is nothing but pi by 4 D square whole square, so area square. So this is what we are writing for V, and then twice G and D. Okay, let us use the same symbol for diameter as we are writing here capital. Let me write here also capital value, capital, because diameter we are writing here as capital D. Fine, at least in this analysis. So now this expression we can write as, say, FL Q square, FL Q square. Well, another D was there here. This is coming from the area, and this D is already there, so this is there. FL Q square, then it is twice G, then we can write pi by 4 square. We can simplify this, but let it be like that. We are not worried for that expression. Then D square whole square, it is D to the power 4, then another D, so it is D to the power 5. Now for a given diameter of pipe, if the diameter of the pipe is given, then if the friction factor of the pipe is known and if length of the pipe is known or given, then for this particular pipe, that means for a given pipe, what we can write that HL, what we can write that HL is equal to, this part we can consider as a constant, this part we can consider as a constant, and we can write K, Q square. Of course, the Hazen-Williams gave this expression not as HL is equal to KQ square, Hazen-Williams gave this as HL is equal to KQ to the power n. And then of course, he said that for turbulent flow, fully turbulent flow, or say for when the flow is moving towards turbulent, then this n value can be taken as equal to 2. And of course, just in lower side the n varies from say 1.8 around to 2. So, that way this n can be very well, for practical purpose we can assume this as 2, because if we consider the head loss to be on little higher side, so far distribution is concerned we will be in safer side. So, we consider that HL is equal to KQ square, n is equal to 2 if we consider, then it become HL equal to KQ square. Okay. And this expression is generally used. So, this is the second condition that we need to satisfy or that we need to know. We have discussed two conditions till now. One is the continuity condition must be satisfied, second is the head loss must be satisfy head loss equation of this Darcy-Weisbach or this Hazen-Williams equation is valid. Well, then the third condition, and third condition is the most important condition for analyzing pipe network. Well, what it states that algebraic sum of head loss around any closed circuit must be 0. Around any closed circuit must be 0. Well, say a flow is occurring in a circuit. Okay. So, this is the circuit. Now, flow is coming from this side and say it is moving this way, then it is coming up this way, and then it is coming this way, and then it is meeting at this point. Well, then what will happen? Well, let me draw another point. This is just one loop I am drawing. Again, if I take this example, there also we can have loop like this, and there can be, suppose I can draw here also one more pipe, say these are pipe like that, and I can put another pipe. So, there will be two loop like that, and from this side the water may be moving out also. Well, like that, similarly here say one loop, and then this is one loop, this is one loop, and this is another loop. Okay. This way the water is going out, Q in, Q out, and there may be another Q out at this point. Well, now this loop, suppose water is flowing from this side, it is going like this, and it is coming like this, and it is coming like this. Now, in this closed circuit, this is a closed circuit. In this closed circuit, if we calculate the head loss, say from here to here we are getting a head loss, from here to here we can see that water is coming, there will be some head loss in this line, then again from here to here there will be head loss. Now, if I try to calculate the head loss around this closed loop, then if we sum up the head loss here, ASL1 suppose, then ASL2, then ASL3, if I sum up all the head loss, then we will be getting that from here to here we have some head loss. Now, when we are seeing from the beginning, say at this point we have some head available. Now, if I just go and turn around the loop and reach here, then head available here will become say H minus HL1 plus HL2 plus say HL3. But we know one point, that in any water distribution system, at a particular section or at a particular point, there cannot be two different head. At a particular point, energy level should be same. So, now what will be the condition? Say from this point we are starting with a available head of h, and then when we are returning to this point we are finding that head available is this much. That means that head loss, what we are considering to be as loss, this must be equal to 0. Head loss around a closed loop must be equal to 0. Otherwise, the condition that head at this point is H initial head, this should be equal to that, cannot be satisfied. If it is to be satisfied, this will have to be equal to 0. So, that is the third condition, and this is the very basic condition which we apply and we try to solve the pipe network problem. In fact, as I said initially, we keep some discharge based on the continuity condition, and then we see that whether the head loss around each of the closed loop, not only in one closed loop, there will be several closed loop in the entire pipe network. So, whether head loss in each of the closed loops are 0 or not. If not, if it is yes, then it is fine, but if not, then we need to apply correction. Well, so let us see step by step what this step may be, that method of solving pipe network problem. Different scientists have attempted solving this problem in different way. So, this complicated problem of pipe network is generally solved by trial and error procedure. Whatever may be the procedure, generally it include the trial and error procedure. Well, and different methods have been developed for solution of this particular problem, and Hardy-Cross, we need to remember this name, Hardy-Cross in 1934 developed the method of successive approximation. They named this method as method of successive approximation. That means it is basically it is a iteration. Initially we assume some value, that is the approximate value we are assuming. Then we are solving it and we are trying it to see whether this condition is satisfied, head loss equal to 0 around a closed loop, and if it is not, then we are getting another approximate value. But how to get this approximate value, that procedure we need to discuss, but we will be getting another approximate value. Then with that approximate value, with this corrected revised value, we will again check whether head loss around the closed loop is 0 or not. So, that is what the procedure is. This method is quite convenient and is widely used even now. Well, of course, some other works are there. Say water distribution system was studied by say McIlroy in 1951. Well, so he studied this McIlroy, he studied in say in 1951 by electrical analogy method. Well, we know that various problem in our hydraulic engineering, particularly say when we talk about flow through porous media, head loss in that case, that we study by electrical analogy method, that is pipe, I mean this is not pipe, what we say that flow net. Flow net, of course, you will have to get the concept of flow net in fluid mechanics or even in soil mechanics, we get this concept, and then there also we apply say electrical analogy method, and here he applied electrical analogy method and he solved this pipe network problem. Then method of equalizing storage was presented by M.B. Mifferson in 1960. And Martin and Peters introduced Newton-Raphson method. Newton-Raphson method is a known method in mathematics, and that was applied for solution of this pipe network problem. Then William in 1973 developed a technique for quick convergence of this cross method and balancing head, cross method of balancing head. So, this method was there, and this method he tried to have quick convergence in this method, and we in 1988 we tried to develop a computer solution of pipe network capable of handling any number of loop. So, whatever may be the number of loop, we just need to give the loop sketch, and then from that by using a computer program we develop, then it can solve the solution for the pipe network by Hardy-Cross method. And then different numerical methods have been used for solution of the pipe network problem, and then nowadays commercially lot of softwares are also available, commercial software are available. I do not want to name these software, but various softwares are available for solution of the pipe network problem. Well, because here perhaps in this class we will not be going into the quite detail of this pipe network analysis, because when we are talking about pipe network, maybe that we are talking about say pipe, simple pipe connecting and then forming a network, but there will be a valve, there will be different other component in between the pipe network. Well, so incorporating all these things, if we try to solve, then of course it become more complicated, and now softwares are available, or simply we can apply our concept and we can develop a computer program for solving this sort of pipe network problem also. Well, then let us see what is Hardy-Cross method, which is widely used and which is very popular till today. Let us start with steps in Hardy-Cross method. Understanding each and every steps in Hardy-Cross method is of course important. Well, first step is that most reasonable discharge in each pipe is assumed satisfying continuity condition. I am repeating this point from the beginning, that first assumed discharge is made or considered based on the satisfaction of the continuity condition. Well, then next step, that is the head loss in each pipe is computed by Hazen-Williams equation, that is K is equal to, head loss HL is equal to K Q to the power n, and this n can be considered as 2 for practical purpose. Next step is the summation of head loss around a closed loop is calculated. Now, at this point we should be careful. Say if we calculate the summation of head loss around a closed loop, and if we just keep on